Welcome to the walkthrough of the 2023 GCSE Combined Science Trilogy Chemistry Paper 2, and we're looking at the foundation tier today. So the first question is all about crude oil, and it says it contains a large number of hydrocarbons. So 1.1, crude oil is a finite resource. What is a finite resource? Well, finite means it's likely to finish, so it means there's only one possible answer. It is a limited resource because we're going to run out of it at some point. 1.2, what is crude oil formed from? Well, it's definitely not from water or from volcanoes, and plankton are little sea creatures which live in the sea, and it's made from man. Question 1.3, what type of substance is crude oil? Now, remember, it's a mixture of hydrocarbons. So there's only one real possible answer there. Now 1.4, the hydrocarbons in crude oil are separated into fractions using fractional distillation, and we need to complete the sentences, and fortunately we're even given the words. Now in fractional distillation, the crude oil is heated so that the hydrocarbons, well, there's only really one possibility, bearing in mind that crude oil is a liquid. It has to evaporate first of all, so we vaporize it. The fractions collect as the hydrocarbons cool, and this is where they condense into the various substances, generally liquids. So 2 marks, obviously those words need to be in the correct order to get both marks. Question 1.5, so hydrocarbons can be cracked to produce more useful molecules. Again, we've got a choice of words to use. Some products of cracking are useful as, well, first of all, alloys are to do with generally metals. Fertilizers, that's more to do with ammonium. Fuels is the best example. We've got loads of examples of hydrocarbon fuels, so very much that answer. 1.6, hydrogen gas is a product of cracking. What is used in the test for hydrogen gas? Now, you can get rid of some of these straight away. Lime water, that's our test for carbon dioxide. Relighting a glowing splint is our test for oxygen. The burning splint, this is our squeaky pop test. So remember, the actual test itself isn't a squeaky pop, it's actually using a burning splint to try and light the gas. So that one can catch people out sometimes. Now, we've got some maths to get into here. So here we've got 5.2 kilograms of crude oil contains 1.53 kilograms of liquefied petroleum gas. Calculate the percentage of LPG, liquefied petroleum gas, in 5.2 kilograms of crude oil. And we have to give our answers to 3 significant figures. So it's worth making a mark there. We need to go back and check our answer and make sure that we've gone to 3 significant figures. So 1.53 of kilograms of our crude oil is LPG, so that needs to go at the top of the fraction, and it's as a percentage of those 5.2 kilograms of crude oil. So that's our fraction. We multiply by 100, and that will give us a percentage. Now that, when you put it in your calculator, is 29.42%. We need to go back and check. We've got to give our answer to 3 significant figures. So if we look at the first 3 figures, we've got 29.4. The fourth figure is less than 5, therefore we round down. So to get our full 3 marks, we need just to answer 29.4. You get 1 mark for showing that part of the calculation, 2nd mark for having that answer, and then your 3rd mark is for correctly answering to 3 significant figures. That whole question's out of 10, so well done if you got 10 out of 10. Right, question 2 now. So this is about the Earth's atmosphere and how it's changing. So gases in the Earth's atmosphere cause changes on the Earth. Draw one line from each change to the gas that caused the change. So where did our oceans come from? Well, they have to have come from water vapour. That water vapour condensed, forming liquid water, the oceans. Now, where do the sedimentary rocks come from? These are things like our limestone rocks, which are made out of calcium carbonate. So it's our carbonate rocks which contain carbon dioxide. Remember, we just draw one line from each change. If we do more than one line, you lose a mark straight away. Right, so question 2.2. So we've got a table of information about the percentage of gases in Earth's atmosphere today and also in the atmosphere of Mars. Which gas has the highest percentage in the Earth's atmosphere? This is just a case of can you recognise numbers. That is nitrogen because it comes in at 78%. A nice easy mark. Now, a bit more maths. Calculate how many times more carbon dioxide there is in the atmosphere of Mars than in the atmosphere of Earth. It's telling us to use the table. Give your answer in standard form. So we need to highlight the numbers. So carbon dioxide on Earth is 0.04%. On Mars, it's 95%. Well, how many times more carbon dioxide is there in the atmosphere of Mars than on Earth? So we need to do 95 divided by 0.04. If you put those numbers, put those numbers in your calculator, you end up with 2,375 times more carbon dioxide in Mars' atmosphere than on Earth. Again, give your answer in standard form. So with this answer, we've got 2 marks so far. We now need to convert that, which means we have 2.375 times 10 to the power of 3. And I suppose it's quite generous, you get 3 marks for that. So remember, you get 1 mark for the calculation bit, 2nd mark for calculating the number, and then the 3rd mark for converting into standard form. Make sure you're comfortable with standard form, whether you're converting from standard form to a regular number or vice versa. Question 2.4. Carbon dioxide is a greenhouse gas. You probably know that already, I'd hope. We've got figure 1. Our graph shows the concentration of carbon dioxide in the Earth's atmosphere from 1960 through to 2020. How has the concentration of carbon dioxide in the Earth's atmosphere changed over that time? We've got to tick one box. Well, our graph is going up. Look at your axes. As time goes on, the concentration of carbon dioxide has gone up. Therefore, there's only one possible option, and that is increased. And then 2.5, another excuse for a maths question. So cars emit carbon dioxide. So a car emits 17.2 kilograms of carbon dioxide on a journey. There's 4 people in the car. Calculate the mass of carbon dioxide emitted per person. Well, that's the total mass of carbon being emitted in the journey. There's 4 people in the car. It really is as simple as putting those numbers in the calculator, and you end up with a value of 4.3 kilograms. That could be as much a maths question as it is a chemistry question. Right, 2.6. Planting trees helps to reduce climate change because trees use carbon dioxide from the Earth's atmosphere. Name the process in trees which uses carbon dioxide. So obviously this is clear overlap with biology, but you do cover it as part of the carbon cycle, and it's a nice straightforward mark. I'm hoping it's photosynthesis. And then question 2.7, a little bit of data analysis. So the graph shows the annual change in forest area in 4 different parts of the world. So you've got the 4 continents: Africa, Asia, Europe and South America. And you've got the annual change in forest area in arbitrary units. Give 2 conclusions about the annual change in forest area. Well, you just need to give 2 possibilities. Now, increases in Africa, you could say it increases in Europe. So you get a mark for each of those, but of course you could also get a mark if you said it decreases in Asia, decreases in South America. So you just need to get 2 of those 4 possible conclusions. There's your 2 marks. Nice, straightforward. And then 2.8, we've got, again, another greenhouse gas is methane. Figure 3 shows the different sources of methane emissions. So you've got other sources, 46%, fossil fuels, 19%, and you've got natural sources, 29%. Landfill is our unknown. We need to determine the percentage of methane emissions from landfill. Now, this is just working on the idea is, do you know that this should all add up to 100%. So if you do 46 plus 29 plus 19, that should give you 94%. The landfill makes up the rest, so it's 100 minus 94 gives us 6%. So again, another kind of maths question squeezed in there. And then final part of question 2. So we've got a diagram shows 2 ways, A and B, of preventing used items going into landfill. Again, we've got some choices to use. We need to name processes A and B. Now, section A, we've got the use part of it, and that's going around in a cycle. So it's going to be reusing. So part A, we need to reuse. And then, of course, part B, we're disposing of materials, and then we're making them back into new materials. Well, that is what our recycling is all about. So again, you need to get those answers in the correct order, but it should be 2 nice, fairly straightforward marks. That whole question, quite a big question, is worth 15 marks, so hopefully you got 15 out of 15 on it. Now, question 3, we're looking at water and the dissolved substances it contains. We've got some apparatus to compare the mass of dissolved solids in distilled water with those in seawater. So we've got the whole method there. Give one safety precaution the student should take. The obvious one here, because we're using a Bunsen burner and we're heating things, is to wear safety goggles, or just goggles. The other possibility could be to tie hair back, which is clearly not a problem for me. Go with safety goggles every time. Alright, question 3.2. So the method used did not give valid results. Which 2 improvements could the student make to give valid results? So again, we're back to this idea of ticking 2 boxes. So there are 2 correct answers. Now, we're trying to look at making sure all the water has evaporated fully. So we need to heat the evaporating basin until the mass doesn't change any longer. That tells us that all the liquid would have evaporated. Leave some water in the evaporating basin after heating. No, that's a load of rubbish, because that would leave some of our dissolved kind of salts kind of in solution, which wouldn't be any good. Record the results in a table and plot a bar chart. Well, that's not going to improve the method. It's a good idea to do that, but it doesn't actually help us. Now, use 25 cubic centimeters of water for each experiment. That seems like a very good idea. It's good control variables. It's a good way, allows us to compare the actual mass of dissolved solids if we're using the same volume of water. Use a beaker instead of an evaporating basin. That's a lot of rubbish as well, because that's not going to change the results at all. So we've only got 2 sensible suggestions there. Again, make sure you're ticking 2 boxes. 3.3, a different student used a method which gave valid results. So now we've got the results. The student concludes that distilled water is pure. Suggest a reason why. Well, in test 1, 2 and 3, there was nothing dissolved in the distilled water, so there were no dissolved solids. That suggests the water was definitely pure. Tap water is potable, and that means we can drink it. One step in producing potable water is sterilisation. So why is potable water sterilised? To improve the taste? Not really sure that's quite the case. Remove dissolved solids, that's not going to do the trick, but it is to kill bacteria. Then 3.5, chlorine is used to sterilise water. The reaction between chlorine and water is reversible. Complete the sentence. So equilibrium is reached when the forward and reverse reactions occur at the same, well, you could say at the same time, but that's not going to get you the mark. You need to be talking about the same rate, the rate at which our reaction is happening. Question 3.6, we've got another one of our gas tests. So we're testing for chlorine, and we're using damp litmus paper. When damp litmus paper is put into chlorine gas, the litmus paper turns. Well, the test for chlorine is to bleach our litmus paper. So chlorine is an acidic gas, it will make it go a little bit acidic, but then it continues to bleach our litmus paper, and it makes it go white. So there's your answer for that one. And then 3.7, we've got a question about adding fluoride ions to drinking water and how it reduces tooth decay. And you've got it's a bit of a data analysis question really. We're looking at the percentage of people showing tooth decay in different age groups, depending on the darker column is if the water's had fluoride ions added to it, and then the lighter colour is water without fluoride ions. We need to compare the effects of adding fluoride ions to drinking water on tooth decay in people between the ages of 25 and 74. Now this is worth 4 marks, so you do need to be adding quite a bit of content. Now, first obvious conclusion would be, if you look at it in every age group, adding fluoride reduces tooth decay. So the dark column is always lighter than the grey column. Generally, the reduction in tooth decay generally increases with age. So tooth decay increases in the 25 to 50-year-old age groups. We actually have a bit of a dip in the 55 to 64 group, and then the tooth decay increases again from the ages of 65 to 74. So you've got that general trend kind of going upwards in terms of tooth decay. Now, not only do you need to be talking about those kind of relevant points from which I've just said, but also you need to start thinking about the magnitude of the change. So adding fluoride to the water probably has the least impact in the 25 to 34-year-olds. It probably has the biggest impact in the 55 to 64-year-olds. So there's quite a difference in numbers there. And then you can talk about actually be specific as well. So use a couple of bits of data. For instance, you could say that in the 25 to 34-year-old age group, tooth decay is reduced by 2%. There's a 2% reduction in that group. Or if you wanted to, in the 65 to 74-year-old group, that difference works out as 7%. So just describing the graphs fully and trying to explain what it shows, you're going to get your full 4 marks with it. So you need to be talking about like the magnitude of the change as well. So there's quite a lot that you could write about there, but it's relatively straightforward. A lot of it is just saying what you see essentially, and you'll pick up the full marks hopefully. And then question 3.8, student A says that water companies should add fluoride ions to all drinking water. Student B disagrees. Now, so we've got to suggest one reason why student B may think that fluoride ions should not be added to all drinking water. Now, if you look at the data, it does seem to suggest it's a good idea to add fluoride, but one of the things it doesn't talk about is adding fluoride ions could be a risk to health. It doesn't look into any kind of side effects, apart from the fact that there's less tooth decay. Could have side effects. So that's another possibility. Remember, you only need one of these answers to get the mark. Could discolour teeth. That's unlikely because you obviously add fluoride to toothpaste and that's used to clean your teeth. And then the final thing is there's an argument that people should be allowed to decide for themselves whether they want fluorine in the water. So anything on those terms is worth 1 mark. In total, this question is worth 12 marks, so if you got 12, well done. Okay, question 4. We're looking at a rate of reaction question. So we're looking at the use of a catalyst to increase the rate of decomposition of hydrogen peroxide. Now, hydrogen peroxide decomposes to produce water and oxygen. We need to write a word equation for the reaction. Now, you just need to look at the previous sentence, and there's your answer. So, hydrogen peroxide decomposes, so it breaks down, so it means that we're starting with hydrogen peroxide, and we're producing water plus oxygen. There's our mark. Don't be tempted to start writing kind of formulas, although they will accept them. The question is actually asking you to write the word equation, so stick to words, makes it much better. Now, the students investigating the rate of decomposition of that hydrogen peroxide using 3 different catalysts. So there's manganese dioxide, there's copper oxide, there's zinc oxide, and they're using a gas syringe to do that. So they're going to be using the gas syringe to measure the volume of oxygen. They'll use a stopwatch to measure it over time, so we can calculate a rate. So question 4.2, we've got the method that the student used. Which 2 control variables are used in this investigation? Now, you need to know your variables. They come up in all the different papers. In this case, we're asking for control variables, and 2 of them. We need to tick 2 boxes. Now, a control variable is something we need to keep the same. The things that we need to control so that it's a fair comparison. Now, the actual mass of the catalyst used has to be a control variable. It would be unfair to use 50 grams of one catalyst and say half a gram of another catalyst. That's just not, you'd be suspicious of the results straight away. Now, looking at the next answers, shape of the flask doesn't really affect the volume of gas being produced, so we can ignore that one. Time of taking the readings. I suppose we would take those readings at the same time, but it's not really, we can still work out a rate of reaction taking them at different times. Volume of hydrogen peroxide solution used. Well, we'd be using the same concentration of hydrogen peroxide solution, we'd also be using the same volume. Volume of oxygen produced, well, obviously that's what we're measuring, so that would be our dependent variable, so that's a load of rubbish. So we have our 2 correct answers there, and it's 2 marks. Right, question 4.3. Now this is worth 3 marks. Now these kind of questions should be almost guaranteed marks. We've got the table of results. We've got the graph plotted for the copper oxide catalyst and the zinc oxide catalyst. We're being asked to plot the data for manganese dioxide. Now, we're going to get 2 marks just for putting our crosses in the right place. Now, you do need to work accurately, and it's pretty much easier to do this on paper. Be careful with your scale. Going up the side, from 40 to 50, that's split up into 5, so each small square is worth 2. So at 60, we're going to 40, at 80, we're going to 45, so that's midway between the 2. 100 is going to be 49, that's midway through that square, and then 120, 120 seconds, we're going up to 50. So we've got 2 marks just by plotting that accurately. You need to be within half a small square to get the marks. So we've achieved 2 marks there. We then need to draw a line of best fit. Now this clearly curves over. We need to make sure we start and go through every point, and you're better off with a slightly wavy line that goes through every single point than using a ruler. Don't be tempted to do a dot to dot with a ruler. You'll automatically lose your mark for the line of best fit. Likewise, don't just draw a trend line with a ruler. This is clearly a curved line. So we pick up our 3rd mark for our line of best fit. Now, question 4.4 is going to ask us which is the best catalyst, and we need to explain why. So we're going to talk you through that question now while the graph's in front of us. Well, manganese dioxide is the best catalyst. That's the one that we've just plotted. Why is that? It has the steepest gradient on the curve. So you can see we're getting a much greater volume of oxygen produced, but the important thing is the gradient of the curve. So if we were going to plot, we're going to rank these in order. Manganese dioxide is the best catalyst, copper oxide would be next best, and then zinc oxide is the worst. We don't have to talk about that. We just have to explain why the manganese dioxide is the best. So we would tick that box, and the reason being we have the steepest curve, steepest gradient, and there's our second mark for the explanation. Alright, and then 4.5, the student repeated the investigation with manganese dioxide catalyst. The results were all close to the true value. We need to complete the sentence. Results that are close to the true value are accurate. Clearly not approximate, because that would suggest that they're all over the place. Alright, question 4.6. The student repeated the investigation using the manganese dioxide catalyst at a high temperature. Complete the sentence. At a high temperature, the rate of reaction will, well, increasing the temperature is one of those other things that increases the rate of reaction. So there is only one possible answer there. It's increase. Now that question is worth 10. Hopefully you got 10 out of 10. Well done if you did. Alright, into question 5. So we've got the combustion of fuels is a source of atmospheric pollutants. So we're talking about methane is a fuel. So this is stuff that comes out of your gas taps. Balance the equation for the combustion of methane. Now there's different ways of doing this. Now with the combustion of a hydrocarbon, I'd always balance carbon first, then hydrogen, and then worry about the oxygens last of all. Now if we've got methane, it's only got one carbon in it. Carbon dioxide only has one carbon in it. So at the minute I would say just leave that bit alone. Carbon suggests it is balanced. Now on the left hand side we've got 4 hydrogens. We're producing water as our product, as one of our products, H2O. Now if we've got 4 on the left, we need 4 on the right. 2 times 2 will give us 4 hydrogens. Now the last bit is oxygen. So if we look at the right hand side, we've got the 2 lots of 1 oxygen there. So we've got 2 oxygens there. Don't forget CO2, 2 oxygens as well. So we have a total of 4 oxygens on the right hand side. We need 4 oxygens on the left. Oxygen is diatomic, therefore we're going to have 2 lots of O2. Now that's the correct way to work this out. It's one of those ones, if in an exam you're in a bit of a panic and you haven't got a clue, and they give you a blank box to fill in like we've done here, generally go with a number 2, and most of the time you'll probably get the right answer. Obviously it's much better if you understand how to do it, but go with 2 if in doubt. Alright, 5.2. Many fuels are mixtures. So petrol and diesel are mixtures of hydrocarbons. And again, we've got a table showing us some of the properties of petrol and diesel. Compare the properties of petrol and diesel. So it's worth 2 marks. Now here, probably the easiest way to go for is to say that the hydrocarbon molecules in petrol have fewer carbons in them than diesel. That's what this bit of the data is all about. And then the other bit of the data, you could say that petrol has a lower boiling point than diesel. And there's 2 marks. You could do it the opposite way, say that diesel's got a longer or a greater number of carbon atoms in the hydrocarbon chain. You can talk about diesel having a higher boiling point as well. But either way, you've got both marks from that. Question 5.3. The gases released when a fuel is burned in car engines may include oxides of nitrogen, carbon monoxide, and water vapour. Which chemical elements do all these gases contain? Well, oxides means we've got things like nitrogen dioxide, carbon monoxide, CO, water vapour, water, H2O. Well, they clearly all have oxygen in them, and that's where you're going to get your mark from. And then 5.4, when diesel burns in car engines, oxides of nitrogen are produced. Where does the nitrogen come from? Well, there's only one possible place. 78% of the air consists of nitrogen. So where else is it going to come from? So, air. Give you loads of space just to write a 3-letter word, but there's your mark. 5.5. When diesel burns, particulates may be produced. What environmental effect do particulates have from burning diesel cause? Now, particulates are the bits of, so it's got very fine dust or soot or basically unburnt bits of carbon. Now, the environmental problem that they can cause is global dimming. You're putting solid particles up into the atmosphere. Now, 5.6. Carbon monoxide may be produced when diesel burns. Give one reason why carbon monoxide is difficult to detect. This is just one of those questions you need to know. Now, carbon monoxide is toxic, but it's tricky because not only is it a colourless gas, so it's a colourless gas, it is also odourless, so you can't smell it. Either one of those answers would get you the mark. And then on question 5.7, explain why water vapour and not liquid water is produced when diesel burns. Well, diesel burns at a high temperature. High temperature, way above 100 degrees centigrade. And if you remember, that's way above 100 degrees centigrade is above liquid water's boiling point. And there's the second mark. Now 5.8, sulfur is a common impurity in diesel. Explain why this causes an environmental problem. So first of all, when that sulfur is burnt alongside the diesel, it forms sulfur dioxide. Sulfur dioxide is an acidic gas which causes acid rain. So that gas gets released, sulfur dioxide, and dissolves into the water vapour in the clouds. And then of course that acid rain will then fall, and you've got a weak acid solution essentially. It can damage buildings, so particularly if you've got limestone buildings as statues, it can damage them, but it can also damage trees and plants which are very sensitive to changes in pH. It also damages aquatic life, so that's things living in streams and ponds and so on. The other thing that sulfur dioxide can do is it can also trigger asthma attacks as well. So that's another possible answer you could give. That's worth 3 marks for that particular part of the question, but in total that question is worth 12 marks. So well done if you got all 12. So well done. Final question on this paper is all about chromatography and how it's used to separate mixtures. So chromatography involves a mobile phase and one other phase. So the mobile phase is the thing that's moving, that's a solvent. What's the bit that isn't moving? Well, that's your paper, that's your stationary phase. Now the question is 6.2, why do the substances in the mixture separate in the mobile phase? So they separate because the substances move at different speeds. They move at different speeds because they have different solubilities, or they might have different attractions for the chromatography paper. Personally, I would say the best answer is that they have different solubilities in the solvent. So different solubilities. 6.3, how many spots will be produced on the chromatogram of a pure compound? Remember, a pure compound only contains one thing. Therefore, you're only going to get one spot formed. Right, so now we've got our maths question. This is calculating the RF value. So in the chromatography experiment, a blue colour moved 4.77 centimetres. The solvent moved 5.3 centimetres. We need to calculate the RF value. So the RF value is the distance the solute travelled divided by the distance that the solvent travelled. So remember, the solvent is the liquid bit, the solute is the colour or the solid. substitute your numbers in. You got 4.77 divided by 5.3. Put those numbers into your calculator and you end up with 0.9 as your answer. And there you are, two nice straightforward marks. Remember, with RF value you should never get an answer greater than 1.0. If you have, you've got the numbers the wrong way round. You can't have your solid moving further than the solvent. That would be impossible. And then the final question, it's a 6-marker, leave the best till last. So black ink is a mixture of several colours. We need to plan an experiment using paper chromatography to separate the colours in the black ink, but don't forget to also how do you identify the colours from the RF values. What I might be tempted to do is actually draw a diagram of the setup here, because it might save you a bit of writing. However, we talk about drawing a pencil line on your piece of chromatography paper, near the bottom edge of the paper. So, like I said, sometimes having your diagram, if you imagine that's our piece of chromatography paper, we've got our pencil line. Draw in pencil because we don't want the pencil's insoluble, and we don't want that interfering with our chromatography. Now we've put a small blob of black ink on the pencil line. So we've got our pencil line, drop of ink on the line, and then we need to have our chromatography paper needs to be put into our solvent. Let's just say we're going to use water as our solvent. So we have our little beaker with our solvent in it. Remember, the solvent level needs to be just touching the bottom of the paper. It certainly shouldn't be above the pencil line. Then you would suspend your bit of paper, kind of on the beaker, make sure it's not touching the sides of the beaker or anything like that, and then we allow a bit of time. So you allow the different inks to separate on our chromatography paper. So we'd leave it, might be 5 minutes or so. At the end of that time, what you would do is you'd have your different droplets. So we'll take that out of the way. So we've got our droplets, so let's imagine we've got those colours. We'd also need to mark the distance of solvent front. That's how far the solvent has travelled. Now we'd then remove this from the beaker, allow it to dry, try not to get it contaminated from anything, so allow it to dry, and then we start taking some measurements. So you'd need to measure the distance of the solvent front, so that's how far the liquid bit has travelled, and we measure that from the pencil line to the solvent front, and then you'd measure from your pencil line to the middle of the first dart, middle of the second dart, we'd measure distance to the third dart. And then we'd use the formula that we used in the earlier calculation. RF value is distance moved by the solute divided by the distance moved by the solvent. And in this particular case, I've just said we're going to have 3 dots formed. We'd end up with 3 different RF values. Now, how do we identify the colours from the RF values? Now, this is, say if we've used, say, water, there will be reference kind of values for these particular inks in water. So we'd then look up the values, the RF values that we got for our 3 different dots, and we compare them with known RF values, and we'll be able to work out from there what the actual colour was and kind of what, or whether it's a certain kind of chemical in particular. Now, to get the full marks on this one, the 5 or 6 marks, you need to make sure that your method is complete and you would be able to calculate the RF values and identify the different colours from those values. So you need to include the calculation part of this, not just how do you separate our different ink. Right, so we've now come to the end of that paper. That question is worth 11 marks. The whole paper is worth 70 marks, so I hope you got 70 out of 70.